Now, what's a good well and what's a bad well? In this case, we're looking at crystalline rock, like granite, not like sandstone that has a lot of pores, but a real hard rock without a lot of pores and definitely low permeability. If you drill a well into solid rock, don't expect to get a lot of water. If you drill a rock or a well where fractures in the rock cross, you can get water even in crystalline rock. Now, under the ground, we probably shouldn't think of it as one aquifer. There are usually several aquifers, or there are often several aquifers, and there may be several layers. In this case, water can take days to get from the surface to the river. If it falls on the surface and has to go through one layer of highly impermeable rock, could take years or decades. And to get down here and back, it could take centuries or millennia. That's thousands of years. This is an uncontained aquifer, and this is a confined aquifer and a confined aquifer. Now, let's move on. Here's what happens in the rainy season. Water table is high, the well is good, there's a spring, this well is good, and you have a river. In the dry season, notice the water table drops. This well is dry. The spring, which is where the water table intersected the surface of the earth, has gone dry, and even this well is lower, and the river is lower. Again, this is showing you the saturated zone, the zone of aeration, or the vadose zone as this calls it, and the capillary fringe. If you've ever stuck a straw into a glass of water and looked, you'll notice that the water creeps up the straw just a little bit. That's a capillary action effect. Sample springs. If you have fractured rock, you can get springs coming out of the fractures. You will see this type of thing occurring up in the McDowells. If you ever hiked to Tom's Thumb from the west side of the McDowells, you'll find this kind of spring. Sometimes you have caverns in limestone, which is very soluble in water, rainwater, because rainwater is slightly acidic after falling through the carbon dioxide in the atmosphere. Here is a spring caused by an impermeable layer, what we've been talking about. And here's a spring caused by a fault. Sometimes we create our own little springs. If we're operating a quarry where we dig down in the ground and we saw rocks out of the ground for countertops or something else, and we puncture the water table, we can create our own little spring. Some wells go dry really quickly. Why? Because they're on a perched water table. A really good well tends to be deep and it will go to the main water table. This is something that happens that people don't think about. And if you live in the northern part of the Phoenix area where you have to pump your own water, it's important. If you pump your water out too fast, you create a very sad cone of depression. And eventually you could cause your well to go dry, at least until this water flows back into the hole that you've created with your well. Here's a typical well operation. Here's what you dig out. And again, here is an artesian well. Okay, here's a bad well. It's drilled in shale. This is a symbol for shale, a mud rock that has very few pores and isn't very permeable. And here's a good well because it's in sandstone. You have to be careful where you drill. Some issues with groundwater. This is a little bit weird, but notice that the water table is slanting this way because the water coming down through the ground is stacked up, and this is the only way it's getting out. Gasoline, which is less dense than water in the old days, and still sometimes, gets out of gasoline storage tanks and gets into the drinking water. Does this really happen? I'll show you in a little bit. We have passed LUST laws, leaky underground storage tank laws. We're digging up the old storage tanks and creating better ones that are lined with little warning sensors underneath. Other countries aren't doing this and their groundwater is being polluted. And once you pollute your groundwater, well, it's polluted. You're going to be drinking gasoline, which is not real good. Ask any of the dead people who can't talk to you about it. Also, chemical companies like to store their stuff. Every once in a while, it leaks. I will show you this happening in the Tempe area. Chemicals that are denser than water will tend to go to the bottom. Here's a leaky underground storage tank. Here are some leaky chemicals. This is really happening. It's not just made up stuff. Here's another typical situation where you have a well with your house, and it's good. Your septic tank, where all your sewage goes, I'll put it that way, and your leach line are down here. If you've done this well, the sandstone will purify the sewage before it reaches the neighbor's well. Yeah, it really does happen. If you don't do a good job, if you're drilling into granite, this can be a problem because the granite doesn't have the aerobic capability to purify this water as it seeps downhill, and your neighbor's well will be contaminated. More issues. All the stuff we throw away eventually will get into our water table. That's why it's important not to throw away chemicals, paints, pesticides, things like that. Not in the landfill, please. We try to line the landfills now, but nothing is ever 100% perfect. Pesticides, heavy metals, all kinds of things will end up going into our water table, and then we pump them out. Again, here's the cone of depression. If you have a little outhouse, your products from that can be going into your well. If you're near the ocean, and this is going to be in one of the movies coming up, I think San Diego County, if you pump out water too fast, you reduce the pressure here, and the seawater ends up coming into your well. You end up with what's called brackish or saline water. What can you do? You can pump fresh water back in and force the seawater barrier back out, making these wells fresh again. Here's Tucson. All these little dots, those are wells. Remember in the very beginning, I talked to you about pumping groundwater and how important it was for Tucson? This is why. Up until the 1980s, they relied 100% on groundwater, and Tucson was sinking because as you pump groundwater out, the aquifer collapses. And once you collapse that aquifer, it is no longer capable of holding, at least in that area, the water that it held before. We have to be careful. This is south of Purgatory, north of Durango, Colorado. And this is a place where groundwater is coming out. It has gone through these rocks over here. It has percolated down through limestone. It has dissolved some of the limestone, or the salts, or the magnesium carbonate, dolomite, and it's coming back to the surface because it is his something very warm. The warm water becomes less dense, like a percolator coffee pot, and it comes to the surface. As the water evaporates, it leaves behind this limestone, and you end up with a rock called geyserite. Here's the geyserite where it's coated a tree that's fallen into it. And you'd think it's really dense, but it isn't. Leaves and little things get in there. Here's a piece that somebody's torn up. It's very porous. And because it has so many minerals in it, butterflies like to drink from it. A few notes on aquifers. This is the Midwest United States. Some of you know what these circles are. This is center pivot irrigation. Shot from, I think, the space shuttle. This isn't from a jet. I have pictures of this one flying over. But you pump your water out of the middle and you spray like crazy. In order to do this, to grow our bread, our wheat, our corn, our soy, we pump huge amounts of groundwater out of the aquifer in the mid-United States. About 27% of the irrigated land in the United States overlies this thing called the Ogallala Aquifer. I think your book calls it the Great Western Aquifer or something like that. This provides 82% of the people who live in that area with their drinking water. And this is kind of sad. This is how much the water table has dropped in these areas. And in some places, it has risen. And in this area, most of this, it has stayed the same. We are overdrawing our aquifers. Here are aquifers in the western United States. Here is the Colorado Plateau aquifer, mostly sandstone and limestone up here with some conglomerates. Here's the Basin and Range aquifer where we live. And we draw our water from soils that are between mountain ranges. Our mountain ranges go way down under the ground, but we don't see it because we're sitting on top of the soils between the mountain ranges. Like this. Pretend like this is Piestewa Peak, this is Camelback Mountain. Phoenix is on top of this. We walk around here not knowing that the stuff we're walking on is actually our aquifer. So we drain our oil into this, we dump our pesticides under our grass, and then we pump the water out of there, never considering what we're doing. It's kind of silly. And again, underneath the ground, there are really old aquifers. Here is the San Joaquin Valley in California, where they've been pumping groundwater for a long time. And this shows how much the ground has collapsed due to groundwater withdrawal. In 1925, this was the elevation of the land. By 1977, the land had sunk that much, or 9 meters, about 30 feet. In Eloy, Arizona, down south of Phoenix on the way to Tucson, we have the same situation going on. A delta, that's a triangle that means the change in from 1952 to 85. The ground here has dropped 15.4 feet. You wouldn't think it's a big deal, but again, you're losing your aquifer, and if you have canals in the area and roads, those end up cracking. Also, we can subsidize farming that goes on there. And this is kind of crazy. Pesticides won't hurt you. It will never get into your body. Probably not the case, because once this rains, this stuff goes down into the groundwater. Cattle are a big issue, because the nitrates and the materials in their feces goes down to the groundwater too. Okay, a few better looks at springs. Here's a typical spring. Humans have discovered it, they piped it, they've lined it. It makes it kind of nice. Here's a little bit more natural spring. If you're a backpacker, a lot of times you will go to seeps, small springs, or regular springs to get your water out for your canteen. And again, here's Roaring Springs on the north rim of the Grand Canyon. Here is a little seep. Where spring isn't so plentiful, that's what you get. And on occasion, you'll get algae growing on this stuff. This is a picture I took in Tairoku Gorge in Taiwan, China. And there are springs coming out past this temple. It is just a beautiful area. Geysers. Here's me a few years ago, hiking on extremely hot volcanic rock, going up to the top of the volcano, and water that has gone down through this basalt turns to steam and comes back up, just like a percolating coffee pot. In this case, Yellowstone. Water has come down. It hits a body of hot rock near a volcanic body or molten rock body. It becomes hot. As it becomes hot, it becomes less dense. The particles are vibrating faster, so they move apart and they rise. And along the way, they bring with them minerals which create these cool colors. On occasion, you get this kind of thing. It is so cool. You get really hot water down here. There's a lot of pressure on it. It would normally boil at 100 degrees or 212 degrees Fahrenheit, but it can't because it's got pressure on it. It keeps building up, and at some point, it pushes out some of the water, which reduces the pressure on this water, which is now maybe 110 degrees Celsius or 230 degrees Fahrenheit. When that water goes out, all of a sudden, this water, which is superheated, which wanted to turn into steam but couldn't because of all the pressure back on it, it bursts out and creates a geyser, pushing the water that was on top of it out. Once it's done that, the water from these pools will begin to percolate back down in again. It will get reheated and repeat the process. As you know, Old Faithful said to go off every hour. Actually, it varies significantly, depending on the conditions of the water on the surface. We will pause there and pick up part 3 in just a little bit, if I can remember how to do this.